Okay, so thank you everyone for joining us on this webinar. My name's Bridie and I'm here to talk you through some of the great new features in our latest release, which is EcoView 13. We released EcoView 13 last month in October 2022, and EcoView 13 includes a great collection of new features, and we'll work through the list shown on the screen during this webinar. And of course, there's a lot more in EcoView 13 than I've listed here, and I'll show you where to find information about other new features at the very end. So we'll start off looking at the Dataflow Toolbox. Now this is a new panel in EcoView, a new pane area where you can have a nice handy interface to make it really easy to add new operators, new lines, scenes, sticky notes, or transducers into your data flow. As you'll see from this little preview on the screen, it's got a favorite section up the top. So if there are certain operators that you create more regularly, you can pin them to the top. There's a recently used section so that you can readily access operators that you created recently. And then we have a nice long list that includes all of EcoView's operators, and below that other object types as well. And what you'll see is there's a little note section at the bottom that gives you information about the object that you've got selected. And if it's an operator, it'll also include the licensing requirements of that operator. Let's take a look in EcoView. So I'll just open up any EV file for this one and show the data flow window. So data flow window, this is where we build all our building blocks for our data processing routine. And on the left here, I've got visible the data flow toolbox. Now you can make this visible most easily by clicking the little button up top here. Click it to turn it off or to show it again. You can also place it wherever you like in the EcoView window, on either side, floating or tucked in with some of the other panels. I'll just make it big here. You can see I've got a few favorites set up. I like to create sticky notes in my data flow all the time. So if I select sticky notes from this list and drag and drop onto the data flow, a new object's automatically created for me. Nice and easily, and much easier than previous approach, which is to right click, new, and select from this list here. Quick and easy drag in. We can do the same for virtual variables. If I wanted to make a background noise removal variable, click and drag. It's created in the data flow, and I can connect it to the input data of interest. And as well as connecting it manually like this, if I select a variable first and then click and drag, it's automatically hooked in as a single step. So this just makes it really easy to build up the important building blocks in your EV file and make data processing just that little bit more efficient. It's also context sensitive. So if I select a different data type, we'll see that the list changes quite significantly. So for GPS data selected, we've only got these 4 options, one of which isn't available because one of the inputs isn't in this EV file. If I click SV, there's a lot more available. Angular data, there's a lot less. And if I have nothing selected, I get to see the full list of different objects that can be created. And anything that's grayed out just means that the type of data that's used as input for that object isn't available. Down the bottom of the list, we have lines, so I can make a new editable line this way. I can also make a new transducer object or start building up a 3D scene window. Click and drag to make it all quite easy. We can also use a little filter box here at the top. If I type noise, I'll see all the operators and objects that have noise in the name. So that makes it quite easy to find something in the list as well. So that's the Dataflow toolbox. While I have this EV file open, I'm also going to show you the file sets window changes. This is a good example. So if we take a look at the file sets window, we've got the list of raw variables that has been extracted from this data file shown here. In older versions of EcoView, this list was a bit of a mess. The raw variables were ordered more or less depending on what order we added them into EcoView's code base. So SV we added a long time ago, that came first. Power we added more recently, that's lower in the list, and so on. So it wasn't very helpful, made it hard to find raw variables here. We've changed this so now it's alphabetically sorted within the different types. So currently I've got it listed by transducer. We'll see T1 and T2, but we can switch to data type. So that will then include power variables, SV variables, movement variables, all lumped together. We can easily disable groups of variables or individual variables. And we can also filter here to find the variables of interest. So that's just a little helpful change to the interface to the file sets window. Okay. Next, we'll have a quick look at image exports. So this makes it really easy for you to generate images of your echograms that you might like to use in presentations, for machine learning purposes, and also to review your data when you have large volumes. And the data review one is, I think, really particularly interesting and useful, and I'll go into a little bit more detail about how we can automate that shortly. But let's just take a quick look in EchoView. In this case, I'm going to look at some Nortec data. So this is the Nortec signature profiler that we added in a previous version of EchoView. In this case, it's a nice upwards looking mooring where this data was kindly shared by the Antarctic Ecosystem Research Division at NOAA. We can see we've got some grid lines here. The data is about 0 meters depth to a little bit over 300 meters depth. And I've also got some grid lines in the time dimension here, in this case 6 hours. This is another new feature in EchoView, which I'll take a little segue to look at. Older versions of EchoView, we only had the ability to show a time distance grid in units of minutes, which if you're working with very long-term deployments was not very helpful to do a bit of maths to figure out exactly how many minutes you wanted for large grids. So now we've added the option to have time by hours and also by days. So that just makes things a little bit easier there. Echogram image exports. In older versions of EchoView, we did this by making a selection in the echogram, right-click, export selection to image. This is a little bit hidden away and also not very easy to use. You have very little control over the resolution. That was entirely decided by how far zoomed into the echogram you were as to what resolution that image came out. EchoView 13 makes this much easier, where we now have echogram, export to image menu options. So through this menu, you can choose to either export the visible echogram, so what you've got displayed on screen, or the whole echogram, which might be a lot more than what you can see on the screen. Then we are presented with a few options as to how we want to arrange and size and scale our export. So we can select a particular range of pings or times if we don't actually want the whole echogram after all. We can select the vertical extent. In this case, I might adjust the depth from all of the data to only 10 meters above the water surface, so minus 10 meter depth. And at the bottom, we also have that image dimensions. So this is the resulting image that we create. I'll start by showing you 1 pixel per sample. Let's create that. Let's call this whole image, and I'll open up the resulting picture. This is quite a long, narrow echogram because we've got a really long number of pixels in the horizontal dimension, but not so many pixels in the vertical dimension. Could be useful in some situations, but what we would want to do here is refine this a little bit more. So let's do the same export again. Minus 10 meters. We use custom image dimensions. So I'll go the same width as the previous export, but let's just make the height a lot higher. The resulting image is now probably potentially a little bit more useful depending on what you're trying to communicate with this image, but you can certainly see a lot more detail at this scale. What you'll also notice is we've got our color scale on the right. This wasn't an option in older versions of EchoView, but of course, the color scale is a really important context for the data that we're looking at on the screen. EchoView will simply export elements like grid lines and color scale and regions and so on, depending on what you've got visible on the echogram at the time. When you're working with large volumes of data, we also have the option to split it by time or by ping number. if I were to split by the 6-hour grids that I've got visible, we can split images by time based on hours. So I'll get 6-hour chunks of data effectively. Let's export that. And what Ecoview is going to create for me is several images, each showing 6 hours of data at a time. Now, this is really neat in particular cases, and this is what I was hinting at previously, automation. So using these image exports in combination with automation is a real game changer, I think. And we go into the details of this in our automation training course, but I'll just give a bit of an introduction to it now, because these new features in Ecoview 13, which includes COM scripting access to all of these settings, makes this really neat. So I'm going to open up some R code to show you. Once I click the right button, there we go. So imagine someone has walked up to you with a nice big hard drive that might have 5,000 or 10,000 or more data files, and they want you to analyze this data. It's a lot of data to be faced with, and you usually need to have a pretty good look at it to see what the nature of the data is, what might have changed over time about the quality or conditions in which that data was collected. And opening up and loading many, many raw files over and over again, bit of a time-consuming process. Data has to be read, different features need to be calculated. And so what we can use here to our advantage is automation. And this is just a simple example script where what this process will do, what this code will tell Ecoview to do, is it'll start Ecoview, it'll make a new EV file based on a template that you've previously set up. So this template could have all sorts of data processing steps pre-prepared, which might include noise removal, could include bottom detection, could include surface detection, exclusions, all of these things. So it can be a preliminary first pass of preparing your data for analysis. We can use that template. We can tell Ecoview to add as many data files to a new EV file based on that template as we like. In this script, I'm using 20. That can be any number, of course. And then once those 20 files have been added, let's export 3 images. In this case, I set it up to do process data. So that's the results of my exclusion lines. Also, I've applied noise removal in my template ahead of doing that. I've got the raw data, and I've also got a convolution of the data, which I find makes it easy to look for problems such as accidental bottom inclusion in the water column and so on. So this script will go through all your thousands of data files, 20 at a time, create 3 images, name them automatically, and then that can just go and run overnight or while you're doing other work, and you can come back the next day and come to your folder full of images. In this case, I've only created 6 images in this demo today, but you'd come back to a folder full of a lot of images, and you can simply use whichever photo viewer you prefer and flick through this and look at all of your data really quickly. The benefit of this is you don't have to get your processing software to load up the raw data and scroll through and wait for calculations. You've just got the images here ready to go. And through that, you can see how well your template's working. If it's not working so well, you can modify it, run the process again, look at the results. So that's a neat part about automation, a bit of a sidestep, but exporting images through COM really makes this quite effective and efficient. So yeah, get in touch if you'd like to learn more about that side of things. Moving on from image exports to machine learning, which is a topic that a lot of people are really interested in. Thank you very much for your interest in this. And obviously, machine learning is a really big topic in a lot of industries and research and so on lately. And that got us here at Ecoview thinking, how can we use machine learning to help people using our software? And ultimately, what we understand it to be is to have the goal of making data processing faster and simpler and easier. Those of you that have used Ecoview a lot will know Ecoview is really powerful. We can do all sorts of things. We can detect all sorts of features in our software. But in a lot of cases, that requires configuring a lot of settings, some of which can be quite complicated, might have trade-offs, and can take a bit of learning to understand how to use them. So our hope is to build a tool, using machine learning capabilities to make data processing easier. And we're going to tackle this by looking at specific challenges and solving those and seeing what's possible. CSIRO here in Hobart collaborated with us, which is awesome. As a result of this collaboration, EcoView 13 includes a trained inference model that can detect a bottom exclusion line in your single beam echograms. And we developed this by CSIRO providing us with a huge volume of EV files that had been manually processed. So EV files set up with bottom exclusion lines in the data that had been scrutinized and expert verified. And in particular, where there are strong fish schools sitting on the seafloor, like you can see in this little echogram snippet here, there would be manual editing required to get the bottom line in the correct position here, just because those schools are so strong. And I'll go and demonstrate this with you in a little more detail shortly. Before I get into that, what we've created in EcoView is a new line algorithm to detect automatically a bottom exclusion line. And we've also got a bitmap operator for visualization purposes. It's all pretty early days and experimental, but we're really happy with how it's going. The capabilities use Google's TensorFlow library and CUDA performance when a suitable GPU is available. If you're experimenting with these capabilities, be sure to have a look at this help file page that I've got the image of on screen, as this includes some instructions that will make calculations much faster. The machine learning algorithms does take a little while to calculate where the line should be from your data, but the overall goal is that although it takes longer to calculate the line than some of the traditional algorithms do, you'll hopefully require less manual editing and fixing of the line detections so that the overall time that you're using is a lot less this new way than it was the old way. So the training data that we used to build the model was Simrad ES60 and ES70 data, and specifically 38 kilohertz SV echograms for that data. And as I mentioned, in the training data, the bottom exclusion line had been defined, and it had also been manually edited when fish schools were close to the bottom. How this model will perform on your data will really depend on how similar it is to the training data, because training data is everything when it comes to building machine learning models. So if you have other ES60, ES70, even EK60 data, pretty similar in characteristics to this training data that we've worked with, your results should be really good. If you start getting a little bit different frequencies, maybe different conditions in the data, different hardware, then your results will definitely vary and may not be as good as they are with the training data. But in the future, we're going to expand the model, build in more types of data and more situations so that it gets more and more successful in a wider range of situations. Let's have a look at it in EcoView. I'll come back to the data flow shortly, and I'll just look at this data a little more closely. If we have a look at this echogram, this is our SV 38 kilohertz data. I've got a line in this echogram already, and this is using one of the old methods, which is the best bottom candidate line pick. This is a virtual line that's just looking for particular characteristics in a window of pings and detecting the bottom. And then I've got just a bit of an offset closer to the transducer face to try and use this as an exclusion line. Works pretty well for most of the data where the schools aren't terribly strong. The distinction's not too bad, could be better. And when we get to areas of data where there's a much stronger school, the results of our exclusion line are not very good. If I was to analyse this data without editing this first, I would be underestimating my school population here. Very much so in this case, and so on. This is a virtual line. This algorithm has properties, settings to configure, quite a few in this case. It's a bit complicated. What we can do is try and improve our results here. I might do that by setting my discrimination level to 35 dB. That improves the results here where this school is very strong, but the trade-off is in other situations, suddenly this line is not so good. It's now dipping into the bottom, where if I undo that change, that worked quite well before, redo, not so good, undo, but we've got the trade-off of the results are good for that school. So this is where our machine learning algorithm comes in, our trained model bottom exclusion line. I'll make that visible. This is the blue line that you can now see on the screen. And we can see that this worked really well where the school is here. In areas of the data where not much is happening close to the bottom, the two lines are pretty similar. Where the school is, much better result with the machine learning approach. Let's just zoom out a little bit. some of these other schools here at the start, capturing the schools that we want to and separating them from the bottom really nicely, which is good. This is really exciting. So if I was analysing this data, what I would do as a next step is set up an intergram display. Now, if you're not familiar with intergrams, what I'm going to do here, let's go through this really quickly. I'm going to set my analysis line to exclude above a linear offset, which is just 0.5 metre above my machine learning line. Exclude above the linear offset and exclude below my bottom exclusion for machine learning. And then on the echogram display tab, we've got these intergram settings here. And I'll click apply. What this intergram is just a running calculation based on these settings, a running calculation of mean SV. And then what I can set is an intergram feature threshold, where I'm interested in the data where mean SV is greater than 30 dB. So if we zoom in on our echogram here, we've got, I'll just turn off my old line first, turn off the best bottom. So we've got machine learning line and that automatic offset. If I right click in the echogram, find next intergram value, what this is going to do is jump to the next part of my entire echogram where it hits that threshold that I've set. So this has highlighted the first one, which is this school. We know that we're happy that this is a school, so the line has performed well, so that's good. Just a really strong school. Next intergram value, this is the same case again. Big, strong school. Next intergram value. Here we've come to a problem bit of data, effectively. Machine learning is good, it's not perfect, and the model that we've got in EchoView does need a little bit more work, which we'll keep improving on. And we can just see in this section of data, the bottom detection failed entirely. I can very easily fix that by just doing a little edit across. Oops. In this case, because we're interested in analysing the schools close to the bottom, I can just draw my line across there and fix that problem instantly. Again, it's a little gap here, draw across, fix the problem instantly again, and so on. And we just have to do this a couple of times in this EV file. While there's still a little bit of editing to be done, even with this new approach, it's a lot less than the editing, especially with the trade-offs that you needed to make with the old algorithm. So that's quite exciting. You can create these lines in two different ways. The first is as a new editable line. So new editable line, dialog that pops up, we can choose pick from current variable, click the properties button here. And then in our lines and surfaces settings here, we just want to choose the new algorithm that we've got available here. So it's a trained model bottom exclusion algorithm, one setting only to configure, and this is just simply a start range. Very, very easy. So we can make a new line that way. That'll go through all of your data, calculate and create a line that you can then just directly edit as you require. Alternatively, we can make a new virtual line. Again, we've got the train model bottom exclusion option in that list. And for the train model bottom exclusion option, we have, again, the same setting, only start range. This will create a virtual line that will only be calculated for the echogram data that you're viewing, just like any virtual line. Can't edit it, so if you need to do editing, then go for the editable line option. So they're the two ways to create that line. And then the third feature that we have in this space is train model bitmap operator. And I'll just synchronize that to this data. The bitmap operator basically is a visualization of what EchoView thinks is happening in this data. So we've set up the model to look at the bottom to try and find that and exclude it. And in this bitmap, everywhere that we've got true values, which is the lighter grey colours, that's the bits of the data that EchoView thinks is bottom. And where there's false values, which is the darker colour, that just means the model hasn't determined any of this data to be bottom. So for some reason, in this particular case, there's a bit of a gap here, and this just means we need to refine the model a little bit further. So that's a good segue into where we're going in this machine learning space. Our next steps are to further refine the model that we've got. So that will be to correct the model, to find places where it didn't work so well, like I just showed you there, and train the model to handle that situation better. And also to add more data sets into our training process. We're also keen to create new models for other features, which could include things like schools in ecograms or individual fish for fish tracking purposes and so on. And so if anybody is interested in this capability and wants to help work with us to make it even better and expand it into the future of Ecoview, please get in touch to get involved. What we're really looking for in this space is large quantity of EV files that have been expert processed, regions have been created or lines have been detected that are accurate and good and that can feed into a machine learning process. So we'd really love to work with folks on that. So please get in touch if that's of interest. So that's our look at machine learning. It's a big fun area. We've really enjoyed getting into it and can't wait to see where it goes. Next, I'll introduce you to some of the new file formats that we've added in Ecoview 13. And let's have a look at some of these in Ecoview. We'll start with Blueprint Subsea Oculus. Now, this is a multi-beam imaging sonar, which some of you may be familiar with these types of instruments. This data was shared by Kevin Webster, formerly of Blueprint Subsea. And what we can see here is on the left, this is the raw data echograms pings that have been extracted from the data file. In the second window, I'm displaying the results of my data processing steps that I've set up in advance, where I'm looking to identify individual fish and count them as individual targets in every ping in this data. And the bottom right corner is a 2D view of that data, so targets over time. Imaging sonar data is really high frequency, really high resolution data. I love it because you can actually see individual organisms, which is really easy for people to kind of connect with and understand what's happening. In this case, we've got some perch swimming around that are chasing, I think, a worm that's been dropped into the water. So they're racing each other to the individual worm. And so we can see Ecoview's algorithms here identifying the different targets, and that'll give us the ability to count individual fish, look at their swimming behaviour and speed over time. So that's one of the fun things with imaging sonar data. The next one on the list, what have we got? R2 Sonic data. R2 Sonic is a multi-beam system, and we're reading raw water column data that can be recorded by these systems using either HYPACK or Quincy to record raw water column data to R2S files. This data was shared by Mike Brissett of R2 Sonic, and what we're looking at here is a simulated gas seep, oxygen release. On the left, we've got the multi-beam echogram as read from file, and then on the right, I've created a maximum intensity virtual variable. This is sometimes referred to as a stacked beams view of the data. But again, it's a 2D conversion of that multi-beam data where we've got range and time. And if I just do a little looped replay here, what we can see just where my mouse is that gas that's being released in this experiment and having a high signal return. So in this case, we could use Ecoview's multi-beam school detection capabilities to analyse that school of bubbles effectively. Next on the list is Simrad OmniSonar data. This is some Simrad MF90 OmniSonar data that was shared by Kongsberg Maritime. OmniSonars have a really huge range and they're often used on fishing vessels or research vessels to try and find schools that are really far away from the ship. Recent versions of Simrad OmniSonars and fisheries sonars include the ability to write data to NetCDF format using the IC standard. And so Ecoview 13 will read the NetCDF versions of the files that are recorded by these systems and includes the ability to do schools detection, region tracking, and so on, and looking at what's happening in the water over great distances. Next on the list is Norbit, a new file, and add the Norbit. Norbit data is another multi-beam. They make Winghead and WBMS systems. This particular data is ISTX 360 model, and it was recorded in an aquaculture enclosure. This multi-beam data was collected where it was attached to the side of an aquaculture pen and was sweeping back and forth, left to right, to try and look at fish distribution within that aquaculture pen and how that changes over time. So it's pretty neat data. That's all the file formats that I'll show you today. I'll just mention that the Norbit Winghead and WBMS data and Teledyne Odom both write to Reson S7K formats. So we've had S7K support in EchoView for quite a few years now, but there's a newer compressed record that we didn't have support for. So we've added that. And thanks to that, we can also read the data that these two hardware models write to. So that's pretty exciting. Finally, on the list, Nortec signature data. We added Nortec signature echo sounder support a release or two ago. And in EchoView 13, we can now read GPS data that's been recorded from signature VM systems that Nortec offer. We'll move on to new operators and with a particular focus on noise estimation and removal. Anyone who's done single beam echo sounder data processing is probably quite familiar with this paper. It's a great one from back in 2007, where Alex de Robertis and Ian Higginbottom described a technique to estimate the signal to noise ratio and to remove echo sounder background noise from your echograms automatically. Quite a long time now we've had a background noise removal operator in EchoView. What we've added in EchoView 13 are two of the intermediate steps described in this paper, which is background noise estimation and signal to background noise ratio. Let's take a look at that in EchoView. If you've ever done one of our training courses, you've probably seen and played with this specific data. What we have here is some 120 kilohertz data that's been collected to really far range. Because it's that frequency and this range, what we see is this TVG enhanced noise that increases with range that results in this lovely rainbow of colour on our echograms. This is obviously a bias that we want to remove before we analyse our data. And so the method that was described in the de Robertis and Higginbottom paper are these 13 operator steps that I've highlighted here. We made that easy with that single one-step operator a few years back now. But there are a couple of other interesting visualizations in this process. First of which is an estimation of signal to noise ratio, which I'm showing here. In this case, we can notice that the color scale is from 0 to 20. And this is a number that reflects the ratio of the signal to the noise for every sample in the echogram. So where we've got the yellows, there's a lot of signal. And where we've got the blues, there's no signal effectively. The other one is an estimate of the actual background noise. So this is looking at that rainbow of TVG enhanced noise that we're subtracting from our echograms. So if you wanted to look at and explore these, you still have to create this somewhat complicated data flow steps. So in EchoView 13, we've made that easy and added some new operators. So I'll select my SV data as input and then type noise here in my toolbox, and I can create background noise estimation. Single step. There we go. We've now got a really easy visualization of that rainbow. We can also, if we want, configure some settings relating to the averaging cell. So over what scale of pings that you want to average and calculate this for. Nice and easy. And again, likewise, signal to background noise ratio. Drop that into my data flow, have a look. Then we just need to change color display minimum to 0, set that back to 20, and I'll go back to color scheme that I prefer, which is Viridis. And so again, we get to see this visualization of signal to noise ratio. So that's quite handy and nice. 3 easy operators, easy to create. We don't need to use this 13-step process anymore. Another new operator that we've added is called transient noise ping removal. And this is complementary to an operator we've already got in EchoView called transient noise signal removal operator that comes from a paper written by Ryan et al. Because we have these 2 approaches now to remove transient noise, we renamed the old one to include signal in the name, and then the new one is ping removal. So this particular approach removes an entire ping if it is assessed as having transient noise. And in terms of how this operator works and the algorithm, it's basically the opposite of the attenuated signal removal algorithm. That one we've had in EchoView for a little while as well. Attenuated signal looks for pings where the signal just drops dramatically compared to surrounding pings. The transient noise ping removal looks for the opposite, so it's just a ping where noise is significantly more than the surrounding pings. What we'll see in this particular example, I've got a single ping with transient noise effectively, which we'd like to remove and not include in our analysis. Transient noise ping removal, drop that into my data flow. Have a look at that same ping, and we can see it immediately picks it up. And in this case, we've got it setting it to no data and removing it from further analysis. If I just zoom back out in this echogram, we'll see it's actually picked up quite a few pings as meeting these conditions, which I haven't changed from the default or done anything clever. And what we might like to do is set up exclusion lines to look only between certain areas of the echogram, or we might like to just adjust some of these settings. If I set this to 90, some of these pings are no longer being removed. I'm still removing a very obviously problematic one. We can choose to set it to no data, or we can choose to replace that ping with a percentile of the surrounding pings, effectively smoothing over it. So just another little tool in the toolbox to try and deal with noise problems in Eureka Sounder data. Now, wideband noise operators. This is very exciting. It's something that we've had a lot of interest in people being able to do, is to assess and mitigate noise in wideband data, which we haven't had in EchoView until EchoView 13. We've effectively solved the maths problems behind the scenes to make this possible. All of our pre-existing and new in EchoView 13 noise-related operators can now take wideband data as input. So that's the list shown on this screen. It's all very exciting, but it does come with a caveat. That caveat is that we don't recommend setting replacement values to no data if you're using wideband data as input. And this is because areas that have no data samples, and this includes bad data regions as well, if that's part of your data processing workflow, they can introduce edge noise and abrupt changes to wideband data, and therefore can have a potentially negative effect on the calculation of wideband frequency response if there's that abrupt change. And that's because you're potentially removing samples that fall into the window of samples that are used to calculate a wideband frequency response. Rather than using no data, we recommend using the smoothing options to smooth over the noise that's found for wideband data. Let's take a look in EchoView. Wideband noise file. This is just some of Simrad's example data here. 2 SV frequencies here, T1 and T2. And if we just take a look at these, they've each got problems that we can deal with now with these operators. In the T1 data, we've got some impulse noise spikes that we would want to remove because these will definitely cause effects in wideband frequency response calculations. And then in this variable here, we can see we've got that rainbow of background noise that we'd like to deal with and remove. Let's take a look at that. So for T1, we want to use impulse noise removal. Drop that into my data flow. These side by side. So the default settings have picked out most of this impulse noise, but I can refine it a little bit more. Change the threshold just down a little. We can see most of these spikes are now being set to no data. So using the no data option just for the purposes of debugging is really helpful because it's obvious to see where they are. Once I'm happy with the settings that I've chosen, we can just replace those noise samples with the mean of the surrounding data. And so apart from that little blip in the first ping, we've tidied up that impulse noise really quite nicely. And for background noise, drop that into my workflow. Just need to configure that a little. In this case, I know because I practiced earlier, I changed my vertical units to a larger vertical extent. Again, that deals with that problem and subtracts it away from the data really nicely. So that gives you lots of new options for mitigating background noise in wideband data. I've showed it for SV data, but this also will apply to your TS data to use ahead of target detection as well. Okay, and finally, we'll have a quick look at the X by Y by Z statistic operator, which I actually had in one of my earlier EV files. That was the Oculus demo. With most data processing, but especially with multi-beam data processing, when you're detecting targets, data smoothing is a really key first step, just to remove and blur out and soften out some of that noise that can make objects hard to detect. If I zoom in on these fish here, we can see they're a little bit patchy. What I've included in my workflow here is the new X by Y by Z statistic operator. Let's just have a look at that side by side. So this is the before, this is the after. Just sort of try to smooth and make those objects easier to detect in the downstream data processing steps. This has a variety of options in this operator. I've used a very, very simple samples within the same beam, 3 samples at the same range across multiple beams and 3 pings. We're looking at those collection of samples to recalculate the middle sample in that 3x3 window. And I've just taken the mean of those, but we also have a lot of other statistics available with some fancier options that can help you to really get some advanced data processing techniques happening. And these statistics are all described in Ecoview's help file on the context-sensitive page, so you can see what they're doing. And so I definitely recommend using these operators, experimenting with the settings and seeing the effects that this has on improving the detectability of targets in your data. That's all I'm going to demonstrate in this webinar today. There's, as mentioned, heaps more new features in Ecoview 13, and I always encourage folks to have a look at our help file page, which contains all the minute details of every single new feature and change of the software. Great detail, so worth sitting down on a Friday afternoon and reading through that. To get the latest version, download it from our website or use the help menu option to check for updates. What you will see only through the check for updates option is the ability to view release notes. In this screenshot I've captured here, I had not yet installed the latest version of Ecoview 13. If I click view the release notes, we can see since the initial release, the 2 updates that we've included and what's been fixed in each of those. So always worth having a look to see what's changed more recently since you last downloaded Ecoview 13 and installing any updates that are available, especially if those fixes are relevant to the work that you're doing. What's next? Currently, we're working hard on development in both Ecoview 13, which will be early next year, and Ecoview 14 that will be later in the year. 13.1 will include some further advances in the machine learning space, also some updates to the calculation of SV of F, which is the wideband frequency response for SV data. That's calculation updates that have come out of a paper for which you can see a preview on the right. It's not formally published yet, but there's archived versions available. We'll make some changes to those SV calculations accordingly. We'll also have some new multi-beam operators, some new support for NetCDF single beam data from both Simrad and Furuno, some additions in the calibration space, and some changes to our analysis options and metrics too. So keep an eye out for that. I definitely recommend either subscribing to our newsletter or watching our social media just to see sneak peeks of these changes and notification of when it's formally available. And with 4 minutes to go, thank you very much for turning up. We're really excited to have Ecoview 13 available and would love to hear your feedback. So please be sure to send it through if you've got any comments on Ecoview 13, or if there's new features in future versions you'd like to see us work on. We'd love to hear your ideas as well. So thank you. And if anyone's got any questions, please pop them in the chat box for me.